a squared equals b squared. Alright, now in the previous session we had a model where the particles were distinguishable. You could tell the difference between any two of them. For the two-particle case, our previous model, we said the two-particle wave function is just the product of the individual wave functions. So psi 1, psi 2. Okay. Now, if you plug this, psi 1, the product, psi 1, psi 2, the individual wave functions for particle 1, particle 2, if you plug that into here and here, it doesn't work. Doesn't fit. Right? You don't get the same thing. So if you assume that your two-particle wave function is just the product of the individual wave functions, that doesn't satisfy that or that. Homework. Right? Convince yourselves of that. Right? So I'll just say it again. So if you're assuming the two-particle wave function is just the product of the individual wave functions for each particle, that does not satisfy that or that, and prove that that's the case. Do that for homework, right? Okay, so we have to, if we're going to get this condition, or this condition, so either that's true or that's true. So for this to be true, if we're going to get a multi-particle system wave function that satisfies this condition for when your particles are indistinguishable, then this is just the simple product doesn't work. That's not going to work. We're going to have to do something else. And here's where it gets weird. Right? Now here's a multi-particle wave function that does satisfy this equals that, and here's another one. There's two of them, so I've got an OR here. So this would be an acceptable multi-particle, well, let's say two-particle wave function. This would be that, right? Or this one. There's two possibilities, and the only difference between them is a plus here and a minus. Now, if you swap around the R1 or R2, you'll just get the same thing. So there's a kind of symmetry about it. So this particular combination it's a kind of sum of products. Okay? A sum of products. Here's a product of two single particle wave functions with psi 1 R1, and here you've got psi 1 R2, and here you've got psi 2 R2, and here you've got psi 2 R1. So it's the sum of two products, and that has the right property that it agrees with this. But so does this one. Now this has a minus, so if you swap around the R's, in other words, you take your two particles and you swap them, so their positions swap, then this whole thing becomes minus. If you put R2 here and R1 there and R2 here and R1 there, you'll get minus what you had at the beginning. Right? So this is a kind of anti-symmetric form. So the plus form here of this sum of products, and here's the difference of products, this form is called anti-symmetric, and this form is called symmetric. So if you have if you have a two-particle quantum system, the two-particle wave function here will have the following form. It'll either be symmetric or anti-symmetric, and you create this multi-particle wave function from the individual wave functions of individual particles. Right? So these wave functions here are wave functions of single particles. Right? But when you go to multi-particle systems, and these individual particles are all identical, you can't tell the difference between them, then you need some weird combination like this for this to be met, this criterion to be met. Now, why 1 over root 2? Well, that comes from the normal. It's just the normalization constant. I suppose you could do that for homework as well. You prove that the normalization constant is 1 over root 2. Okay, now I've just said that before, that the plus case here is called symmetric because there's a symmetry about these two, and the minus case here called antisymmetric because when you swap the particles around, you get minus this result. Okay, now so I'll shorten the antisymmetric case as just A/S, so antisymmetric, right? Now watch what happens in the antisymmetric case. Say your two particles have the same state, in other words the same eigenfunction. So in other words psi1 equals psi2, right? Well if psi1 and psi2 are the same, if these two are the same, then this product cancels this product. You get nothing. So your two particles wave function, psi here, gives you 0, gives you nothing. So what happened to the particles? So they disappear? Or? So this leads in, so you effectively, for the antisymmetric case, you just can't get that. You just, because if you do have two identical particles with the same same state, right? Then the two particle wave function becomes 0 because it's the antisymmetric case, right? That's the case where you have the minus, the two product terms with a minus, and if the two product terms are equal, well, they cancel each other. So the two particle wave function is 0. Now this there's a lead into what's called it's rather famous. It's pretty well as famous as the Heisenberg uncertainty principle, the HUP. Well, this is the PEP, the PEP, the Pauli exclusion principle. And what it says is that, well, I've said it before, but I'll spell it out now. So the PEP, the Pauli exclusion principle, more or less equally famous with the Heisenberg uncertainty principle, not with the general public, but certainly amongst quantum mechanics, the specialists, because of its huge consequences, which I'll mention a little bit later. So the Pauli exclusion principle says that for antisymmetric particles, those that obey this multi-particle wave function, they cannot, underline the word not, they cannot have the same wave function. They cannot be in the same state, any two of them. Because if they are, then the multi-particle wave function is 0. Right? So particles just disappear. Well, that's not allowed. The conservation of particles, in a sense. Now later we will, when we get into quantum field theory, things get a bit more complicated. But for the moment, let's keep things simple. It's undergrad level. Okay, right? So that's the Pauli exclusion principle. You cannot have antisymmetric particles that obey this, have a wave function of this form. You cannot have antisymmetric particles that have the same state. Right? That's the PEP, the Pauli exclusion principle. And it was created. Pauli created because he was puzzled. He's trying to figure out. He was looking at Bohr, B-O-H-R. Now remember, he was a disciple of Bohr. Bohr invited Pauli and Heisenberg. They stayed a lot at Bohr's Institute of Theoretical Physics in Copenhagen. And those two were the most famous of Bohr's disciples. I mean, they both made huge contributions to theoretical physics and quantum mechanics. Like, they were both genii. Well, all three of them were genii. I mean, Bohr was right up there with Einstein. I mean, he was a match for Einstein. But Pauli, for example, when he was 21, he wrote an encyclopedic article on Einstein's general, not special, general relativity that to this day is still a masterpiece. 21, right? So obviously a genius. So anyway, Pauli was puzzled. He was trying to figure out why don't all the electrons occupy the ground state of the hydrogen atom, for example, or the ground state of any atom? Why don't they all? Why are there like inner orbits and outer orbits? Why is that the case? And he, to explain that, he came up with his PEP, the Pauli exclusion principle.